Hello all. Let us start discussion on a new paper, Modern Physics. When I say modern physics, you may think, what are the modern concepts in physics? When it has started? What are the old concepts in physics? We will quickly go through all these doubts. The post-19th century can be considered as the era of modern physics, while the physics before 19th century is treated as classical physics. Modern physics began in the era of 19th century with Max Planck's discovery of the role of energy quantization in blackbody radiation. Of course, that was really a revolutionary idea, and it is soon followed by Albert Einstein's masterpiece work, Theory of Relativity and Quantum Theory of Light. Classical physics is inadequate to explain the behavior of particles of microscopic size, such as electrons in atoms or nuclear particles. For such small-scale phenomena of atomic and nuclear physics, new theory is proposed, which is known as the quantum theory. And again, classical mechanics is inadequate in the case of relatively high-speed particles. When we say high-speed particles, we should note that the speed is in the order of velocity of light. There, we need to replace the classical mechanics by theory of relativity. So we can say that modern physics incorporates the elements of quantum physics and relativity. And you have already started learning quantum mechanics from our faculty. And here you are going to learn about special theory of relativity and a bit information about atomic nuclei and radioactivity. Let us start talk about relativity, more precisely special relativity. The first point you should understand that all motion is relative. The speed of light in free space is the same for all observers. We have to look at this point very carefully. The quantities such as length, mass, and time interval are considered as basic quantities in elementary physics. But when somebody started measuring one of these quantities, no special point is made about how these quantities are measured. So, we may have the questions like, do these quantities change while an object in rest or in motion with relatively high speed? Do we really care where the measurement have taken? To answer these questions, first of all, we need a reference frame. With respect to that frame, we are measuring the quantities. So let's see frames of reference. A passenger moves relative to an airplane. The airplane moves relative to the earth. The earth moves relative to the sun. The sun moves relative to the galaxy of stars, and so on. So here we can see that everything is moving with respect to the other one. So we should fix the frame of reference. In simple words, we can define the frame of reference. A frame of reference is a set of coordinates which can be used to determine the quantities such as position and velocity of objects in that frame. So from the concept of relative motion, we can make a point that different frames of reference move relative to one another. We understood from the above examples that in each case, a frame of reference is a part of the description of motion. So to say something is moving always implies a specific frame of reference. There are basically two kinds of frames of reference. The first one is inertial and the second one is non-inertial. Let's see what are the difference between these two kinds of frame of reference. Take the first one, where the law of inertia is valid. And the second point is, an object at rest remains at rest and an object in motion continues to move at a constant velocity if a force acts on it. The third one is that all inertial frames are equally valid. These three are three important points in the case of inertial frames of reference. Now look at the second kind of frame of reference, the non-inertial frames of reference, where the law of inertia doesn't hold. And also, any frame which is accelerating either in the linear or rotating around some axis is non-inertial frame. So these are the important points regarding inertial and non-inertial frames of reference. So keep in mind that all inertial frames will move with respect to the other one with a constant velocity, and it will not accelerate and it will not rotate. The relative motion between the objects leads to the point different frames of reference move relative to one another. I can say a bus is moving with respect to me, or a bus is moving with respect to the ground, or a bus is moving with respect to the bus stop. So everything is relative, which means there is no absolute motion. And everything is relative motion. So from this concept, we can say that there is no universal frame of reference that can be used everywhere. And the special theory of relativity deals with the consequence of lack of these universal frames of reference. Before moving on to the core of relativity, let us clear the concepts of space and time. How scientists treated space and time in classical physics and how scientists treated them in modern physics. More precisely, we can say how Newton treated space and time and how Einstein treated them. So, space and time are important in relativity. If the question is, where do things happen, we will say that's in space. And we usually represent a space with the coordinate x, y, z. And if the question is, when do things happen, then we have the answer in time. And usually we represent it in t. Since we are dealing with relativity, let's see how the coordinates of an event E transform from one reference point to other. Here I remind you that when I say a reference frame, please keep in mind that are inertial frames of reference. Let us take two inertial frames of reference S and S dash. Let S dash is moving with a constant speed v relative to S. If an event E has coordinate x, y, z, t in S, what are its coordinate x dash, y dash, z dash, t in S dash, where the event is the combination of space and time. And we can represent an event with space and time as x, y, z, and t. Here you can see two frames of reference, and both are inertial, where the frame of reference S dash is moving with the velocity v with respect to this frame S. And you can see an event E, which can be represented x, y, z, t with respect to the frame S, and x dash, y dash, z dash, t dash with respect to the frame S dash. And now we will see how Newton and Einstein relate these coordinates. First, we will take the Newton concept of space and time. According to Newton, space is absolute, which means the space remains always similar and immovable. The space is very rigid, according to Newton. And also, time is also absolute, which means if you measure time from any two frames of reference, that will be same. That is, t dash will be equal to t, like x dash equal to x in the case of space. And also he made that the space and time are independent. And also the space and time are unaffected by the events occurred in it. So if we follow the Newton concept, we can see that Maxwell's theory is not consistent with Newtonian mechanics. From the Newtonian concept, Galileo made his transformation from one coordinate frame to other one, which is known as the Galilean transformation, shortly GT. According to Galileo, the space is not absolute, which implies x dash equal to x minus vt, y dash equal to y, and z dash equal to z. But according to Galileo, time is absolute, which means t dash equal to t. That means if you measure time from any reference frame, which will be same. And the other point is that Maxwell's equation is variant under GT. In the Galilean transformation, you have seen that x dash equal to x minus vt, y dash equal to y, z dash equal to z. Here you may have the question that why y dash and z dash is not transforming like x dash? Because while we are considering the frames of reference, for our convenience, we have assumed that origins of the two frames of reference coincide at t equal to 0. The second point is that both the coordinate frames are parallel. The third point is that velocity of the second frame with respect to the first one is v along the x-axis. So due to this assumption, y dash and z dash is not transforming like x dash. So here you have seen the transformation from the coordinate system s to the coordinate system s dash. Similarly, we can transform the coordinates from s dash to s, which is called the inverse Galilean transformation. In the inverse Galilean transformation, x equal to x dash plus vt, y equal to y dash, z equal to z dash, and t equal to t dash. The length of an object or the distance between 2 points is invariant under Galilean transformation. The length of an object is invariant under Galilean transformation, which means L dash will be equal to L. Distance between any 2 points is also invariant under Galilean transformation. From the inverse Galilean transformation, we have R equal to R dash plus Vt. So if you take the derivative on both sides, you will get dr by dt equal to dr dash by dt dash plus v, which implies u equal to u dash plus v, which is called the velocity addition in Galilean transformation. But if you take the acceleration, which you can see invariant under Galilean transformation, which implies a dash will be equal to a. So the length and the acceleration are invariant under. So the Galilean transformations are based on two assumptions. The first one is there exists a universal time t, which is the same in all reference points. And the second point is that the distance between 2 points in various inertial systems is the same. So any two events occurs simultaneously for any observer in the case of Galilean transformation. And also all the laws of Newton, that is the first, second and third, are invariant under Galilean transformation. So far we have seen the Galilean concept regarding space and time. Now we will look at the modern concept, which means the Einstein concept of space and time. According to Einstein, the space is flexible, the time is changeable. Space and time should be considered together. Space and time are affected by events, motion, and action occurred in it. Space and time are two parts of one whole concept called space-time. And last one, according to Einstein's view, we are all traveling to a combination of space and time. And the important fact is that the Maxwell's theory is consistent with special theory of relativity, which was proposed by Albert Einstein. So Einstein concept replaces the concept made by Galileo. The Galilean transformation is a good approximation at relatively speed, which is much smaller than the light velocity. Of course, Albert Einstein was a genius and his way of thinking is so much appreciable. On 1905, he published his special theory of relativity. Let us have a look on the two major postulates of special theory of relativity. And we should note that the special theory of relativity is only valid for inertial frames of reference. The first postulate is that the laws of physics are same in all inertial frames of reference. And the second one is that the speed of light in free space has the same value in all inertial frames of reference, which is approximately 3 into 10 power 8 meter per second. So these two are the major postulates of special theory of relativity. And all the phenomena which we are going to discuss is in accordance with these two postulates. Lorentz concept regarding space and time is in accordance with the Einstein concept of space and time. Now, here we will see the Lorentz transformation, which replaces the earlier Galilean transformation and which is in good agreement with STR. According to Lorentz, space is not absolute and time is also not absolute. Now we will look at how the coordinates are transformed in Lorentz transformation, where x dash, y dash, z dash and t dash are the coordinate in S dash frame, and x, y, z and t are the coordinates in S frame. Now we will see the relation between S and S dash frame. X dash equal to gamma into x minus vt, y dash equal to y, z dash equal to z, and t dash equal to gamma into t minus vx by c square, where gamma equal to 1 by root of 1 minus v square by c square, which is equal to 1 by root of 1 minus beta square, where beta equal to v by c. This is the transformation from the reference frame S to the frame S dash. Now we will see the inverse Lorentz transformation, which is basically the transformation from the coordinate system S dash to S, where x equal to gamma into x dash plus vt dash, y equal to y dash, z equal to z dash, and t equal to gamma into t dash plus vx dash by c square. In Lorentz transformation, the Maxwell's theory is invariant.